In this video, we will see two more problems on potential gradients. So next we will move on to after solving this problem, we will move on to new topic, that is energy density and electric dipole. So before going to that, we will solve two problems, and if possible, we will see in this video we'll start the topic, or in next video we'll start next topic. So if you, the given problem is, for a potential field V is equal to x square y minus 5z, determine the following at a point P of minus 4, 3, 6. First we have to find is electric field intensity, second one is electric flux density and volume charge density rho V. So given potential is V is equal to 2x square y minus 5z. So using potential gradient equation, gradient of V, using that relation between the electric field intensity and gradient V, we can write E is equal to minus del V. So V E is equal to electric field intensity is equal to minus of gradient of potential. So which is equal to del V can be written as dou V by dou x into Ax cap plus dou V by dou y into Ay cap plus dou V by dou z into Az cap. So V is 2x square minus y minus 5z. So substituting that and differentiating that. So in the place of v, you will substitute 2x square minus y minus 5z, and here also, and differentiating with respect to x, y, z, you will get minus 4xy into ax cap plus 2x square ay cap minus 5az cap. Now to find electric field intensity at a particular point, we will substitute the coordinates of point in the equation of electric field intensity. So in the place of x, y, z, we will substitute minus 4, 3 and 6. So in the place of x, we will substitute minus 4. In the place of y, we will substitute 3. And in the place of z, we will substitute 6. Then you will get equation for electric field intensity as 48 ax cap minus 32 ay cap plus 5az cap. This is the first question. What is second question? We have to find flux density at D. To find flux density at D, we will use the relation between electric flux density and electric field intensity. So we know that D is equal to epsilon naught into E. So you know that D is equal to epsilon naught into E. So what is E? E is 48 in Ax cap minus 32 Ay cap plus 5Az cap. So multiplying this equation with the epsilon naught, you will get point D is equal to 0.425 Ax cap minus 0.283 Ay cap plus 0.044 Az cap nanocoulomb per meter square. Now third question is, we have to find volume charge density rho V. So relation between rho V and the flux density we know using Maxwell's equation or Gauss law in point form. Rho V is equal to del dot D. Rho V is equal to del dot D. So what is D? D is epsilon naught E. So E is given as minus 4xy Ax cap plus 2x square Ay cap minus 5Az cap. So here I'll keep D as epsilon naught into minus 4xy Ax cap minus 2x square Ay cap plus 5Az cap. Now rho V is del dot D. So del dot D can be written as dou by dou x into dx plus dou by dou y into dy plus dou by dou z into dz. Now according to this equation, what is dx? Dx is epsilon naught into minus 4xy. What is dy? Dy is epsilon naught into minus 2x square. Similarly, what is dz? It is epsilon naught into 5. So substituting that in this equation and then differentiating with respect to x, y and z, you will get epsilon naught into minus 4y plus 0 plus 0. So at point 3, what is the value of y? Y is equal to 3. So substituting y is equal to 3, you will get minus 12 epsilon naught. So rho v is equal to, substituting value of epsilon naught as 8.854 into 10 to the power minus 12. So you will get rho v is equal to minus 0.1062 nanocoulomb per meter cube. So this is how you find the electric field intensity and electric flux density and volume charge density in a given point for a given equation of potential using potential gradient equation. So we will see one more problem on this. in different coordinate system. Then we will move on to next topic. So next problem is, the statement of the problem is, find the potential and the volume charge density at P of 0.5, 1.5, 1 meter in free space, given the potential field as under. So first potential equation is given as V is equal to 2x square minus y square minus z square volts. And second equation is given as V is equal to 65z volts. So we have two equations here. So we have to find potential and volume charge density at point P. So when this is the equation for potential, and other cases when this is the equation for potential, what is the value of V and rho V at point P. So first we will take up this first equation, that is V is equal to 2x square minus y square minus z square. What you have to find? You have to find potential at P due to this equation. Now to find potential due to this equation at point P, so substitute in this equation V is equal to x square minus y square minus z square. Substitute x is equal to 0.5, y is equal to 1.5 and z is equal to 1. So substituting that, you will get potential at point P, which is equal to minus 2.75 volts. So potential at point P of 0.5, 1.5, 1 is minus 2.75 volts. Now how we can find electric field intensity? Because we have to find volume charge density. To find volume charge density, we need to know what is electric flux density. To find electric flux density, that is D, we have to find what is electric field intensity, that is E. So electric field intensity can be obtained by relation between E and potential gradient, that is E is equal to minus del V. So del V can be written as dou V by dou x into Ax cap, dou V by dou y into Ay cap plus dou V by dou z into Az cap. So you know that V is equal to 2x square minus y square minus z square. So substituting the V and differentiating with respect to x, y, z, you will get you have to do partial differentiation. So integration of 2x square minus x y square minus z square with respect to x will be 4x. Partial differentiation of 2x square minus y square minus z square with respect to y will be 2y, and partial differentiation of 2x square minus y square minus z square with respect to z will be 2z. So you will get final equation as equation for E will be 4x minus 4x into x cap plus 2y into ay cap plus 2z into az cap whole per meter. Now we have to find electric field volume charge density. We have to find D, because using Maxwell's equation we can obtain volume charge density. So Maxwell's equation is rho V is equal to del dot D. So D we have to obtain. So D can be obtained using this relation. D is equal to epsilon naught into E. So D can be written as epsilon naught into E is minus 4x into Ax cap plus 2y into Ay cap plus 2z into Az cap. Now using Maxwell's first equation, rho V is equal to del dot D. So which can be written as dou by dou x into dx plus dou by dou y into dy plus dou by dou z into dz. So we know that dx is equal to, what is dx? Dx is minus 4x and dy is 2y and dz is 2z into epsilon naught. So partial differentiating that term with respect to x and y and z, so you will get minus 4 epsilon naught plus 2 epsilon naught plus 2 epsilon naught. So you will get the volume charge density due to the potential equation V is equal to x square minus y square z square at point P is equal to 0 coulomb per meter cube. This is how you will obtain volume charge density for a given potential equation. So this is first case. What is the second case? V is equal to, when V is equal to 65Z volts. So to find, same way we have to proceed. To find, first we will find, so here it should be 6 rho phi z, not 6 phi z. So we given equation is 6 rho phi z, because this is in which coordinate system now? Rho phi z means it is in cylindrical coordinate system. But point P, X, Y given in Cartesian coordinate system. So we have to convert these Cartesian coordinates into cylindrical coordinates. So we can obtain phi z, which is equal to z, which can be retained as it is. Phi can be obtained by tan inverse of y by x, which is equal to 71.565 degree, and r can be obtained by rho can be or r or rho can be obtained by x square plus y square, which is equal to 1.5811. Now to convert this phi, keep it in phi in radian, so that our calculation will be in SI units. So I have to convert this into radian. So to convert that phi into radian, I will be multiplied by pi by 180. So I will get 1.249 radians. Now substituting this in above equation, you will get potential at point P as 11.8492 volts. Rho is equal to 1.581 and phi as 1.249 volts and Z as 1. So substituting that, you will get potential at that point as 11.8492 volts. Now to find volume charge density, I have to find rho V, which is equal to del dot D. So to find D, I have to use potential relation. I have to find what is electric flux density, electric field intensity E, using potential gradient equation. So E is equal to minus del V. So partial differentiating this V equation with respect to R phi Z. So del V can be in cylindrical coordinates. Del V can be written as dou V by dou rho into AR cap plus 1 by R into dou V by dou phi into A phi cap plus dou V by dou Z into AZ cap. V is 6 rho phi Z. So substituting and taking partial differentiation here with respect to R, if you take partial differentiation, this will be 6 phi Z into AR cap, and here with respect to phi, if you take partial differentiation, you will get 6 RZ by R into A phi cap, here 6 R phi into AZ cap. So simplifying this, you will get 6 minus 6 phi Z AR cap minus 6 Z A phi cap minus 6 R phi AZ cap. Now to obtain electric flux density using the relation between electric field intensity and electric flux density, so we can write V is equal to epsilon naught into E. So substitute E and keep it as it is, as R component, phi component and Z component. Then use the Maxwell's first equation, that is rho V is equal to del dot D, and you know that in del dot D can be written in cylindrical coordinate system as 1 by R into dou by dou R into R dr plus 1 by R into dou by dou phi into d phi plus 1 plus d by dou by dou Z into dz. So dr component is minus 6 phi Z and d phi component is 6 Z and dz component is 6 R phi. So substituting that and obtaining partial differentiation, you will get rho V is equal to 6 phi Z epsilon naught into R. So substituting values of 6 phi, what is phi, what is Z and R in this equation, you will get rho V is equal to, minus 41.96 picocoulomb per meter cube. In next video, we will see the what is energy density and what is electric dipole. That is the last topic in first part of the second module. Then we will see the second part of the second module is capacitors and dielectric material.